All right, so section 2.3, we are now to a very important section, kind of a turning point in this course. Pretty much the rest of this course will be kind of based on this foundation that we're going to lay in this section 2.3. In the first two sections in chapter 2, we're leading up to this. This is kind of the most important, at least conceptually, the most important section that we're going to look at. So we're not really learning any new math per se, but we are learning a new concept, and the new concept is going to carry over for the rest of the chapters, chapter 3, 4, and 5 that we're going to be doing. And so let's review a little bit what we talked about with the average rate of change in 2.1. So the average rate of change of y with respect to x over some interval x1 to x2. So how is y changing as x is changing from x1 to x2? And so if we look at some curve, we have some curve like this, we can look at the average rate of change from this point over here to say this point down here, and we can draw the secant line between those 2 points, and that will tell us the average rate of change. In this section, we are interested in the instantaneous rate of change, which is essentially going to move this point along the curve until we approach the original point. And so we're going to shrink that interval. So the average rate of change over some interval, we're going to shrink that interval. So we call that the instantaneous rate of change of a function f at the input value x1. And we're going to use what we learned in the last section, which is the limit. And I don't know why it's doing that. So we're going to take the limit as x2 approaches x1 of this quotient here. So the limit of f of x2 minus f of x1 over x2 minus x1. And so what that does, as x2 approaches x1, as we move this way, what is the slope of that line right there at that point? So the slope is kind of always changing, because here it's increasing. Eventually we get to a point where we're decreasing. So we're talking about a positive slope here. We're talking about a negative slope going down this way. We're talking about a positive slope here. We're talking about a zero slope right here where it's changing at the bottom here or at the top. But with this formula, we can find the instantaneous rate of change at any point along this curve. So there are actually two ways to express this. So an alternate way is if we let x1 equal a, and then we use h to represent the length of the interval, so delta x. So delta x would equal h, or that would be x2 minus x1. Then we can take the limit. But now, if delta x is h, we're essentially here shrinking delta x. So we're taking this difference to 0. And so if we're taking this difference to 0, we're taking delta x to 0. Well, that's the same as taking h to 0. And actually, before we do that, let's kind of derive this difference here. So let's start with delta y over delta x. Delta, that's not an a, that's a delta. That is, of course, f of x2 minus f of x1 over x2 minus x1. And recall, we talked about this with average rate of change. This is essentially just a slope formula. So we have the change in y over the change in x. So this is just a slope formula. We're just kind of getting a little bit, we're using function notation, essentially. So if x1 is a, and the difference from x1 to x2 is h, then x2 would equal a plus h, right? So f of x2 would be f of x plus f of a plus h. F of x1, because x1 is a, this would be, oops, that should not be a minus there, or an equal, it should be a minus. F of x1 would be the same as f of a, and then x2 minus x1, which is delta x, that is going to be replaced by h. So this is another way to express this. That is an a plus h. This is an alternate way to express this. Sometimes it's easier to use the first way, sometimes it's easier to use the second way, but you want to be comfortable with both of them. And then we can turn this instantaneous rate of change at the input value x1 into the instantaneous rate of change at the input value a, which of course a is x1. And we're just going to take the limit of this. So the limit as h approaches 0 now. So h approaching 0 is the same as x2 approaching x1. Or we could say delta x approaching 0. That'd be the same thing as that. That'd be the same thing as this. So the limit as h approaches 0 of f of a plus h minus f of a over h. And so this formula and this formula are equivalent. They are doing the same thing. They're both measuring an instantaneous rate of change at some point on the curve. And we'll use both of these. Some of these examples we'll do both of these formulas. So the first example we'll do before we end this video is find the instantaneous rate of change of x squared at x equals 3. And so we'll do both formulas. So let's do limit as x approaches 3. So 3 is the initial point, and this would be f of x minus f of 3 over x minus 3. All right. And we'll kind of divide this in half. We'll do the other formula over here. So let's plug everything in. Limit as x approaches 3. F of x is x squared. F of 3, so now plug in 3, and we have 3 squared, which is 9. So that'd be x squared minus 9 over x minus 3. And now we just need to simplify this because, like we learned in the last section on limits, if you plug in an x, or you plug in a value for x and you get 0 on the bottom, 0 on the top, you cannot evaluate it that way. So we have to simplify this. We have to change something in some way. Last time we saw that maybe you can factor it, maybe you can rationalize the numerator or the denominator if you have a square root. In this case, no square roots, but we can factor the top into x plus 3, x minus 3. And then, of course, we see that the x minus 3's will cancel. And we're left with the limit as x approaches 3. And this, of course, is a continuous function. And so we can just plug in the 3 for the x, and we get 6. And so the instantaneous rate of change of x squared at x equals 3 is 6. And so that's using the first formula that we used, where x is approaching some number. If we look at the other one with the h, so the limit as h approaches 0, f of x plus h minus f of x over h. Now, in this case, we're plugging in 3 for the x. So you kind of got to get used to the subtle differences. You got to plug the 3 in somewhere. And h is going to go to 0, so it doesn't make sense to plug 3 in for h. So that leaves the x. If you have trouble remembering, so things like that might help out. So if you have trouble remembering where to plug in the 3 or what to do with the f of x, because over here we leave the f of x, the x is in there. Over here we don't have the x, we have the h instead. So f of x plus h, we're going to plug, and actually we could do 3 plus h minus f of 3. So we're going to plug in the 3 for the x, and now plug in what we get from this difference quotient. So f of 3 plus h, so we're going to plug 3 plus h in for x. So we have 3 plus h squared, and then f of 3, like I said last time, is 9, and that's over h. And then limit as h approaches 0 FOIL this out. So we have 9 plus 6h plus h squared minus 9 over h. The 9s will cancel out. We can factor out an h from what's left. I don't remember if this may have been 2.1, probably was where we did the difference quotient. If you remember, whatever that was, whichever section, we talked about whenever you're doing this difference quotient, which we didn't do the limit earlier when we did that, we just did the difference quotient. But whenever you're simplifying this, any terms without an h in the numerator are going to be canceled out. So you should just be left with terms with an h in the numerator, and then you can factor them out like we're going to do here, and then that will cancel with the h on the bottom. So we have the limit as h approaches 0 of 6 plus h. We can just plug 0 in because this is continuous. We can plug in the 0 and then we get 6. And we should, we already know the answer was 6, but this is just another way to get it. So when you do these, you don't necessarily have to do both unless it specifically asks you to do both somehow. But you should get the same thing because they're doing the same things. Just sometimes one is easier than the other. And that kind of comes with experience, knowing which one maybe to use over the other one. But for the most part, they are equivalent. And for the most part, one is not going to be any easier than the other. It's just maybe which one are you used to using. But they are the same, and you want to be comfortable working with both. So we'll look at some other things in the next video.